Space is vast. It's full of mysteries that have intrigued humanity for centuries. From the twinkling stars we see every night to the distant galaxies that are barely visible through our most powerful telescopes, the universe is a treasure trove of wonders waiting to be discovered. Some of these mysteries are visible to us if we know where to look. With the right tools and knowledge, we can uncover secrets that have been hidden for eons. Among these mysteries are Einstein's cross and Einstein's ring. These fascinating phenomena are named after the legendary physicist Albert Einstein, whose theories have revolutionized our understanding of the cosmos. These phenomena are not objects themselves, but rather illusions created by the universe. They are visual tricks that occur due to the bending of light. They are illusions caused by the bending of light, a consequence of Albert Einstein's theory of general relativity. This theory explains how massive objects can warp the fabric of space-time. Imagine a distant galaxy, so far away that its light takes billions of years to reach us. This light travels across the vast expanse of space, carrying with it the history of the universe. Now imagine that light passing by a massive object like a cluster of galaxies on its way to Earth. This massive object acts like a cosmic lens, bending the light around it. The massive object warps the fabric of space-time around it. This warping effect is what causes the light to bend, altering its path. This warping bends the path of the light much like a lens bends light. The light's journey is altered, creating a new path that leads to fascinating visual effects. The result of this bending is that we see multiple images of the distant galaxy, or we see the galaxy's light smeared out into a ring. These images are not just beautiful, they are also scientifically significant. These are the phenomena known as Einstein's cross and Einstein's ring, respectively. They are named in honor of Einstein's groundbreaking work in theoretical physics. They offer us a glimpse into the distant universe and provide clues about the nature of gravity itself. By studying these phenomena, scientists can learn more about the structure and behavior of the cosmos, helping us to understand our place in the universe. Gravitational lensing is one of the most fascinating predictions of Einstein's theory of general relativity. This phenomenon allows us to observe the universe in ways that would otherwise be impossible. It occurs because massive objects warp the fabric of space-time around them, creating a sort of cosmic magnifying glass. Imagine space-time as a stretched sheet. If you place a bowling ball on the sheet, it will create a dip. This simple analogy helps us understand the complex nature of space-time distortion. This dip represents the distortion of space-time caused by the bowling ball's mass. The greater the mass, the deeper the dip. Now imagine rolling a marble across the sheet. If the marble comes close to the bowling ball, its path will be bent by the dip in the sheet. This is similar to how light behaves when it passes near a massive object in space. This is analogous to how light, traveling through space-time, is bent by the presence of massive objects. The light doesn't travel in a straight line but follows the curvature created by the mass. The more massive the object, the greater the bending of light. This effect is most pronounced near extremely massive objects like black holes and galaxy clusters. This bending of light can have some pretty amazing effects. It can distort the images of distant stars and galaxies, creating fascinating visual phenomena. In some cases, it can create multiple images of a single object. This is known as an Einstein cross, where a single quasar appears as 4 distinct images. In other cases, it can magnify the light from distant objects, making them appear brighter than they would otherwise. This allows astronomers to study objects that are otherwise too faint to observe, and in some cases, it can even create arcs or rings of light. These are known as Einstein rings, where the light from a distant object is bent into a complete or partial ring by the gravitational field of a massive object. Einstein's cross is a striking example of gravitational lensing. It is located in the constellation of Pegasus, about 5 billion light-years away from Earth. At its heart lies a galaxy known as Huchra's lens. This galaxy is so massive that it acts like a giant lens in space. Behind Huchra's lens lies a quasar. A quasar is a very energetic and distant active galactic nucleus. As the light from the quasar travels towards us, it passes by Huchra's lens. The massive galaxy bends the light, creating 4 images of the quasar around the galaxy. These 4 images arranged in a cross-like pattern give the phenomenon its name. Einstein's cross is a beautiful example of how gravity can warp our perception of the universe. It reminds us that the cosmos is full of surprises, and that even the seemingly impossible can be explained by the laws of physics. Einstein's cross is more than just a pretty picture. It is a valuable tool for astronomers, providing insights into the distribution of matter in the universe. By studying how the light from the quasar is bent by Hucra's lens, astronomers can map the distribution of mass within the galaxy. This information is crucial for understanding the nature of dark matter. Dark matter is a mysterious substance that does not interact with light, making it invisible to telescopes. However, it does interact gravitationally, and its presence can be inferred by its effects on visible matter. Einstein's cross provides strong evidence for the existence of dark matter. The amount of bending observed in the quasar's light is far greater than can be explained by the visible matter in Hucra's lens alone. This suggests that the galaxy is embedded in a halo of dark matter, which contributes to the lensing effect. Section 5. Einstein's ring, a cosmic halo. Einstein's ring is another spectacular example of gravitational lensing. It occurs when a distant source of light, such as a galaxy or quasar, is perfectly aligned with a massive object in the foreground, such as another galaxy. The alignment has to be precise. The massive object acts as a lens, bending the light from the distant source and focusing it towards Earth. Because the lens is circular, the bent light forms a ring-like structure around the lensing object. This ring, known as an Einstein ring, can be a perfect circle or slightly distorted, depending on the alignment and masses of the objects involved. The size and shape of the ring provide valuable information about the mass of the lensing object. This allows astronomers to study objects that would otherwise be too faint to observe, revealing the properties of galaxies and galaxy clusters in the distant universe. Section 6. Cosmic Magnifying Glass, the significance of Einstein's ring. Einstein's ring is a powerful tool for cosmology. It acts as a natural magnifying glass, amplifying the light from distant objects and allowing astronomers to study them in greater detail. This magnification enables us to probe the early universe, observing galaxies that formed shortly after the Big Bang. By studying the properties of these distant galaxies, astronomers can learn about the conditions in the early universe and how galaxies have evolved over time. Einstein's ring also provides a way to measure cosmic distances. The amount of bending depends on the mass of the lensing object and the distances between the source, lens, and observer. By carefully measuring the properties of the ring, astronomers can calculate the distances to the source and lens. These distance measurements are crucial for determining the expansion rate of the universe and understanding the nature of dark energy. Section 7. Examples of gravitational lensing. A glimpse into the distant universe. The universe is teeming with examples of gravitational lensing. One of the most notable is Abell 1689, a massive galaxy cluster located about 2.2 billion light-years away. This cluster is so massive that it creates a complex web of distorted arcs and multiple images of background galaxies. Another striking example is SDSS J1004+4112, a quasar located about 7.5 billion light-years away. This quasar is lensed by a foreground galaxy cluster, creating 5 distinct images of the quasar. These examples, and many others like them, provide stunning visual evidence for the theory of general relativity and offer a glimpse into the distant universe. Section 8. Conclusion. The universe's grand spectacle. Einstein's cross and Einstein's ring are more than just curious phenomena. These fascinating cosmic structures are formed by the gravitational lensing effect, where the immense gravity of a massive object, like a galaxy or a black hole, bends the light from a more distant object. This bending of light creates multiple images or rings, offering us a unique window into the universe's hidden depths. They are testaments to the power of gravity and the elegance of Einstein's theory of general relativity. This theory, which revolutionized our understanding of space and time, predicted such phenomena long before we had the technology to observe them. The precision with which these predictions match our observations is a powerful confirmation of Einstein's genius. They remind us that the universe is full of surprises and that our understanding of the cosmos is constantly evolving. Each new discovery challenges our preconceptions and pushes the boundaries of our knowledge, revealing a cosmos that is far more complex and wondrous than we ever imagined. These cosmic spectacles offer a glimpse into the distant universe, allowing us to study objects and phenomena that would otherwise be beyond our reach. Through the lens of powerful telescopes, we can peer billions of light-years away, witnessing the universe as it was in its infancy and tracing the evolution of galaxies over cosmic time. They provide crucial insights into the distribution of matter in the universe, the nature of dark matter, and the expansion rate of the cosmos. By studying these gravitational lenses, we can map the invisible dark matter that makes up most of the universe's mass and measure the rate at which the universe is expanding, shedding light on the mysterious force known as dark energy. As we continue to explore the universe, we can expect to find even more examples of gravitational lensing, each one revealing new secrets about the nature of gravity and the evolution of the cosmos. These discoveries will not only deepen our understanding of the universe but also inspire future generations of scientists and explorers to look up at the night sky with wonder and curiosity. Let us continue to gaze in awe at the wonders of the universe, inspired by the knowledge that there is still so much more to discover. The universe's grand spectacle is a never-ending story, one that invites us to keep exploring, learning, and marveling at the beauty and mystery of the cosmos.